So here's the questions. So where are we? Well, we've made a lot of progress, but one of the things that I'm struck by, talking to my students and trying to advance their projects with them, is that we're in the era of very large language models, and there's a lot of magical thinking about what those models are doing. So my students tend to sort of think that they're doing everything, and that all you have to do with these models is show them a few examples of what you want them to do, and that will point them to the area of their memorization of text that will deal with the problem. And I find myself having to say to my students that I don't think that that's necessarily going to work, particularly for the problems that we're looking at. And I'm going to argue that where we should be is combining the things that we learned when we used to think in terms of logic-based or structurally based, symbolic-based methods, and we have to integrate those with language model-based methods. Language models are very good at telling you what unseen examples are most similar to in your training data, but I don't think that that's a substitute for structured models, and in particular in question answering, I don't think it's a substitute for inference from one state to another. And so my talk is really going to be about inference in question answering. And the way I'm going to argue that we should get there is, first of all, getting away from logic as it's developed by logicians, who really have very different questions in mind. Also, by making the logic scale to the kinds of problems that we're dealing with when we deal with question answering from text. And by exploiting the way that language models actually work. I don't think it's wise to think that language models must be inducing the kind of structures that we use to solve these tasks ourselves. I think there's every indication, and I'm going to briefly refer to some of our work kind of probing this question. I think there's every indication that language models, large language models, simply work in a quite different way from the way that we work. And we shouldn't waste our time trying to show that they have the same kind of internal structure as ourselves, because they're just doing it a different way. And the different way that they're doing it is immensely powerful and can be leveraged to do things that we can't do any other way. These models are here to stay, but I think that we must find out what they're actually doing and exploit their strengths, rather than thinking that they must be learning hidden syntax and semantics and even inference. And I'm going to argue that the inference is really the weak point of the large language models. So very briefly, looking around the audience, I wasn't quite sure who the audience were going to be. So I think the motivation is probably very obvious to the audience that is actually here. But I'll say it anyway. Most information that we need to answer questions that we can't answer just by thinking about them is out there somewhere on the web in the form of text or spoken natural language, rather than as structured data, as knowledge graphs like Freebase and the rest of it. Even in knowledge graphs and databases, there's very often a free text comment field for entering information that doesn't fit into the existing data structure. In other words, something that you've noticed that you couldn't get into the standard record structure. And very often, that is the most interesting part of the database entry, because it points you to the way the database is going to change in future and the new things that it's going to have to represent. So we would like to get these natural language data into databases or knowledge graphs using natural language processing, because they're sitting there in free text. We would also like to interrogate and update these data structures in natural language. And that is a very difficult problem to solve, as the previous talk made quite clear. Because the problem of open domain question answering is that there are always too many ways of asking and answering the same question. So it's very rarely the case that the form of words that the user chooses to ask the question is actually anything like the form of words that the answer is latent in the text that is being queried. So I'm going to start with a toy example, and it is a toy example because I'm going to use it as a running example to try and make the ideas that I'm going to present concrete. You want to know who played against Manchester United last night. And the text says that Arsenal beat Manchester United, or Manchester United's defeat by Arsenal is referred to. Arsenal obliterated Manchester United. It can say all sorts of things. So if you just naively build, you're sitting there looking at your news feed, and you're building a knowledge graph with some kind of parser, some kind of low-level information extractor of the kind that was applied in the early days of Mark that we heard about in the previous lecture. If you just build a knowledge graph based on those relations found in the text, which when I was a graduate student, we called a semantic network, an object-centered graph, you won't be able to interrogate it effectively because of the mismatch, the impedance mismatch between question and answer. Conversely, if you build a knowledge graph using a graph queried language relations, such as the ones that you find in Freebase, then querying it to with natural language, you can train an end-to-end model, but it will need to be robust to the same variation in natural language input. Now, for this toy example, of course, you would just Google the question, and you would get back a set of snippets from which you could work out the answer to your question. All that stuff about Arsenal beating Manchester United would tell you that who Manchester United played. But that doesn't always work. So if one of the questions that I came across actually quite a while ago, but it still is the case that it fails, is what are Miles Davis recordings without Fender Rhodes piano? And if you do that, you get back a set of snippets. You can't read them, but these are the ones I got back. And they're all about records by Miles Davis with Fender Rhodes piano, which is what you don't want, or about Fender Rhodes piano, which you probably also don't want either. What is the problem here? Well, the problem arises from the lack of a usable natural language semantics. And all that work in symbolic frameworks a long time ago really didn't produce a usable natural language semantics. It's just too big a question, too big a problem for us to do common sense inference on the basis of. And there are two modern solutions to that problem. And I'm going to talk about them both in the remainder of the talk. One of them is to use a pre-trained language model as a sort of latent natural language inference data set, as a latent entailment graph, that it's seen so much text that it knows that being defeated by somebody, if you're a sports team, entails playing against them. The other solution is to try and induce something more old-fashioned, a structured entailment graph from text by machine reading, and to just read so much text that you work out that if two teams are in the defeat relation, then somewhere else in the text you read about them playing against each other. If you read about somebody being elected president, then you also read about them running for president. So if the question is who ran for, when did Trump run for president, you can work that out from the fact that he was elected. So I'm going to talk about these two solutions to the problem in the remainder of the task. The basic encoder-decoder architecture in NLP that was deployed in the last talk we inherit this from machine translation. and it offers a very general method for sequence-to-sequence alignment. And this method, of course, can be used to learn semantic parsers as direct transducers from natural language meaning to meaning representations such as a graph query language. That has been a very successful approach. It only sort of works because this approach, which avoids the use of a grammar entirely, is very bad at generalization. So if it's presented with a sentence in which a relation that it's seen many times is presented in conjunction with some entities that it's seen many times, but it hasn't seen the relation and the entities in that combination, then it fails to generalize very spectacularly. And a major cottage industry at the moment that many of my colleagues at Edinburgh, and indeed I myself, are working on is the problem of compositional generalization. How can you get these models to know what to do with unseen combinations of seen elements? Of course, unseen combinations of seen elements is exactly what grammars were invented for. They are invented for compositional generalization. And in fact, my colleagues are trying to re-import notions that are very like grammar into these sequence-to-sequence models. They can also, of course, be used as a closed model for question answering by masking during training. And that's a sensationally effective way of answering questions, provided those questions have been asked before, and the answer is to be found in the large amounts of text that the large language model has been trained on. So these are examples of the kind of successes and some of the errors that are characteristic of these models. Can they be used for text inference? In other words, can they be used for bridging between the fact that the text talks about defeat and your question was about the event in the first place, the playing event that beat event entails? And Heinrich Schütze and his students have been working on this by methods like fine-tuning large language models on entailment data sets and also probing with things that might be found in the text that suggest the entailment relations. I'm going to argue that this is not clearly an approach that is working so far. Heinrich has had some success on this, but it's the evaluation of supervised text inference, in other words, text inference done by fine-tuned large language models, is really an open problem. Natural language inference data sets like SNLI and XNLI and the rest of them are riddled with artifacts that machine learning can learn as a proxy for the task that you're really interested in, which is entailment. This is partly because the data sets that they're trained on also fail to include the false inverses of directional entailment. Playing doesn't entail being defeated in a match, but being defeated in a match entails playing. And large language models, if you're not very careful, will treat those two questions as the same and will give the same answer depending on the data. So I'm going to cut this short because I'm running out of time. Our probings of Heinrich's model and other models of text inference, supervised models of text inference, suggest that actually these are not learning anything directional at all, and that large language models are really working on the basis of memorizing the training data. If you've got a trillion parameters, and you know these days it's even more than a trillion parameters, you can memorize the training data. And they excel at tasks where the memorized text actually contains something similar to the question. And for natural language inference, it's likely that the training text doesn't include explicit sequences like this happened, therefore that happened, or this happened because that happened, which is a sort of probe that might work for inference. So I'm going to talk in the remainder of the talk about an unsupervised method where we don't rely on having human annotated inference data sets to train on. So we're going to build a large unsupervised natural language entailment by parsing large amounts of multiply authored text about the same events. So at the moment, this has to be news text because there are lots of newspapers writing about the same events because the people are interested in the same things. And one newspaper article will say that Manchester United played Watford, and the other will say that they beat Watford or were beaten by Watford. So we learn from such observations that if we read about a statement about, if we look at the overlap between the pairs of entities that are involved in one type of event and the pairs of entities that are involved in another one, then we will be able to infer the entailment relation between those events if it exists. And I'm going to tell you briefly about some stuff that I've been doing over the last few years, where we've done this in English and in Chinese. And this is the work of, I should have said on my first slide that this is all the work of my students. And I'm going to mention them by name as we come to them. Javad Hosseini did the early work on building these entailment graphs. And this method, which I've described to you very briefly, and the details are in the paper, but essentially it involves reading large amounts of text for coincidences in statements about the same named entities. This method scales, so we practice on a corpus of news data, which is 20 million sentences. But when we really want to satisfy ourselves that the thing is working, we have a much larger data set. The 20 million data sets is the news spike corpus from Seattle. And we have our own corpus, which we are about to make available, which is an order of magnitude larger. But the problem with these things is that an order of magnitude larger data set for this method doesn't buy you that much. It buys you a just noticeable difference in coverage and accuracy, both. But it doesn't solve the problem of the Zipfian distribution of the relations that we're looking at. So the problem that this method faces is sparsity. It's high precision, because if you find an entailment rule this way, it probably is sound. But we have a problem with recall. So the thing that I'm going to talk about in the rest of the talk is whether we can smooth entailment graphs with non-directional language models. I'm going to assume that language models are essentially associative, and that what they are essentially learning is this multi-dimensional, very large dimensional sphere of similarity relations, where the radii of the sphere are dimensions of similarity. Maybe there's even a syntactic dimension of similarity in there somewhere. But it is similarity of association, similarity of text, that the two things occur in, or the things occur in, the relations you're interested in occur in this large amount of text. So can we use this method that I'm assuming is essentially non-directional to smooth the directional entailment graphs? And can we do that without losing the directional precision of the precision of indirectional entailment? I'm going to skip over these two slides because I don't think they're that relevant to what I'm talking about. These are just statistics about this method. And really, the only thing to say about this is that these things are large, but they're not large enough. So we've done it for the news spike corpus of 20 million sentences, the news crawl sentence an order of magnitude bigger than that. And this is some statistics. There are some, you can think of it as a collection of typed subgraphs. So there's a person-person type graph, a person-organization type graph. And there's some statistics at the bottom of the slide about the size of the entailment graphs that we are dealing with. And there's a few very large entailment graphs because of the weakness of the type system that we're using. The only thing, other thing I'll say is that this is a completely transferable method. If you have a named entity recognizer and a sound parser for your language and a corpus of news, you can just apply this technique out of the box. Well, I say that, but my student Teddy Lee did this. It took him about a year to do the first version of this thing there's a smaller and a larger Chinese news corpus. And these are the same statistics about it. It's actually a slightly stronger graph than the one that we built for English. And the reason it took him any time at all was that he had to do some actual intellectual work with the tools, because everything in Chinese is predicated on the assumption that Chinese is just like English, and you can transfer all the stuff you did in English to Chinese, and that just isn't true. And in particular, the parser was no good, and the named entity recognizer was no good. But apart from that, this is a transferable method. But it's sparse. So the rest of the talk is going to be about smoothing that graph. I'm actually running a little short of time. What's the weakness of this thing? Well, I'm going to talk about the premise and the hypothesis, because that's the vocabulary that is used in the text entailment, the text inference data. But for our purposes of question answering, the hypothesis is the question, and the premise is the thing that is actually in the text. So you've got a text, you made it into a knowledge graph offline, in a few minutes offline, in order to work with it. And there's a premise, you have a question, and you have to say, is there a relation in the text that answers to this question, even if it's not an exact match for the question or hypothesis? Now, if the premise in the text and or the hypothesis, the question, is not in the entailment graph, then you're finished. All you can say is, I don't know. Because the entailment graph has nothing to say. And that makes you think of soft methods, large methods, like large language models, and whether they can do anything to help. In particular, if we can find a premise prime, P prime, or a question prime, H prime, that actually are in the graph, then if the P prime that we found is entailed by the premise in the text, or the H prime that we found entails the question in the text, it's actually asymmetric. Then if P prime entails H prime is in the graph, then by transitivity of entailment, the premise in the text does entail the answer to the question H. Otherwise, you should answer no, because you should believe that your method is complete. Or maybe you should answer, I don't know. The idea, and this is the work of my current student, Nick McKenna, is that what we should do is we should rely on the machine reading-based entailment graph whenever it has an opinion about the answer to the question. But if either the premise in the text or the hypothesis, the question, are not in the graph, or both are not in the graph, we should use a large language model to find a P prime and an H prime that actually are in the graph, and or an H prime that are actually in the graph. And then if either the premise or the P prime that we found, or the H prime that we found, and the H or the H are in the graph, then we can answer the question. So this minimizes the non-directional influence of the language model. And I'm assuming, as I say, that it's really based on similarity. This is not a very good slide. I grabbed it from the paper. We have a paper in submission, and I think it's on archive, in fact. What this slide says is that if the text said, the question is, did Arsenal play Manchester United? Just a yes-no question for simplicity. The text says Arsenal obliterated Manchester United, et cetera, and obliterate is not in our graph. So what we do is first we use the language model to embed the predicate that is missing from the entailment graph, namely obliterate, to find the most similar one. In fact, we do this offline using contextualized embeddings. So for the predicates that are in the graph, we actually find nearest neighbors to obliterate using the language model. And in the last step, the entailment graph itself completes the directional inference. And if that doesn't do it for us, then we give up. But actually, the entailment graph doesn't contain defeat. That is a nearest neighbor of obliterate. And in the entailment graph, among other things, defeat entails play. So we have an answer to our question because we found a P prime that was in the graph as entailing RH question. So we say, in fact, we can say more than just saying yes. We can give an explanation. We can say the reason that we're answering yes is that we think that Arsenal defeated Manchester United on the basis of this question of the entailment graph. So there's a little bit of explanation going on here as well. So here's some details about what I just described. I think that this just sort of says everything that I said before, except that it raises the question that there is no guarantee that the language model K nearest neighbor P prime, that was defeat. There's no guarantee that obliterate actually entails defeat. It's just the language model that thinks that they are very similar in their associative properties in the text. So we're taking a gamble here, because if obliterate does not entail defeat when we're talking about sports teams, then our assumption of transitivity of entailment is unsound. So is this going to work? Well, it turns out that it worked. It partly works. So this graph, the dull gray dotted line, is the entailment graph. The entailment graph on its own, with none of this enhancement. I can't do this. None of the enhancement by the language model. The green line, the green line is the smoothing effect, the effect of smoothing the premise. In other words, the effect of believing that if defeat is a close neighbor of obliterate, then it's entailed by obliterate. And that actually works right across the domain. You can see here a sort of reification of the weakness of the entailment graph on its own, that at the high precision end, it's pretty good, but it loses recall. So by the time it gets to 50% recall, it's at 50% precision. That is what we're trying to smooth away. However, the magenta line shows that language model smoothing is actually deleterious for smoothing the hypothesis, the question, right across the whole range. So why is language model smoothing asymmetrical for the premise in the text, but you shouldn't do it with the question? The answer is that there's, and this comes to my point of sort of using the language model for what it's actually learning. There is an oddity about the distribution of the words that the language model is building a similarity sphere, a similarity model on the basis of, which is that there is an increase in specificity. There's a sort of inverse relation between specificity and frequency. So the more just to simplify, the more frequent a word is, the more general it is, the more frequent a word is, the more specialized it is, and the more general the word is, the lower its frequency. I've got that, I keep getting that the wrong way around. The specific terms are low frequency, and the general terms, the more general terms are high frequency. So the words like dachshund are lower frequency than words like dog. Now, there's a sort of refinement to this point, which is that once you get to natural kinds like dog, then words start getting less frequent the more general they are. So there are fewer occurrences of vertebrate than there are of dog. But for the purposes that we're thinking about, the dominant influence is that if you look at the k-nearest neighbors of a word in the language model, you will get more frequent words because they will be the words that the language model has a lot of evidence for. So you will tend to get generalizations. And this is a very general technique with language models of all kinds. You see it in translation, that translations tend to be blander and more general than the text that you started out with. This is a well-known bias. And what it means is that when the language model finds nearest neighbors of the things that are in the graph, then it very often ends up with more general words than the missing P, the thing that is in the text that you're asking yourself whether it entails an answer to the question. Now, since specifics are often hyponyms, so dachshund is a hyponym of dog, and related generics are hyponyms, like mammal, it's likely that P entails P prime if you take it as the nearest neighbor in the language model. So what this says is that you smooth the premise, the thing that is in the text, you're likely to get a generalization of the thing that is in the text, the relation, the word that is in the text. And if you get a generalization, it very often entails the thing that you started off with. So being a dog does entail being, being a dachshund does entail being a dog. So if you find out that being a dog entails whatever you're interested in the question, I'm skipping from entities to relations in a very free-handed way, then the answer to your question is likely to be reliable. However, by the same reasoning, the nearest neighbors of the question, the hypothesis, that are most likely to be in the entailment graph and are going to be the highest probability as neighbors, they are going to be hyponyms of the hypothesis. They're not going to be hyponyms. So they're not going to be things that are entailing of the hypothesis. They're likely to be things that are entailed by the hypothesis, but that's not what you want. That's going to be unsound. So the remainder of the talk I'm going to skip over because we've sort of tested the hypothesis that this is what is going on by using some certified hyponyms and certified hyponyms to smooth the premise and, most interestingly, the hypothesis. And what we find in this experiment, which you'll have to look on archive to find the details of, are that if you smooth the hypothesis with hyponyms. In other words, you don't just use the language model and get the most frequent things, which are likely hyponyms. You actually use things that WordNet tells you really are hyponyms of the hypothesis. Then you get an effect of smoothing on the hypothesis. It's a rather odd effect. It's a very slight effect if you just smooth the hypothesis on its own. But if you're also smoothing the premise, then smoothing the hypothesis actually is a very strong win across the board. And that is the black line that is showing on both of these graphs for premise smoothing and hypothesis smoothing. I'm going to wind up because I'm out of time. The conclusion of this is that you can smooth entailment graphs with language models on the premise or antecedent side, the text side. Whether you can also smooth the hypothesis on the consequent side, for instance by using WordNet, is an open question. We've shown that if you do that, on a certain entailment data set, you get the effect. But it's an entailment data set that we constructed to be adversarial using WordNet. So we actually don't know whether this is going to work in the field. And actually, I'll tell you that I doubt whether it will, because WordNet is constructed essentially by hand and is also sparse. So I suspect that in the field, using WordNet to smooth won't work. So what we're actually looking at is, as an alternative, because we're going to do that, but we don't think it's going to work, is to bias the language model in its generation of k-nearest neighbors towards hyponyms. We're going to try and teach it that it should be going down the generalization hierarchy rather than up. Whereas for the premise, we're going to teach it that it should go up rather than down. So we're actually looking at the language model on its own to see whether it is capable of doing this task if we train it the right way. I personally, being a romantic of the old school, am very skeptical about that. I think we're still going to have to use the entailment graph for its precision, but we will tell you about that at a later date. Thank you.
Thank you, Mark. This is a great presentation, great work. Regarding the recall issue, do you think if we combine between the entailment graph and have embeddings for the predicates of the nodes, while still keeping the relationship between the predicates for the precision, but we are adding to the representation of the predicates, which is the embedding from the language model, do you think this could help on the recall issue?
Yeah, well, I think it helps on the generalization. It helps you. That's what we're actually doing. I didn't spell it out, but when we find the k-nearest neighbors to the word, so we're looking for something in the text that is missing from the graph, obliterate. We look at offline, we have looked at all the nodes in the entailment graph, and we use contextualized embeddings. I mentioned it in passing, but it probably wasn't clear. We use contextualized embeddings in making the estimate of the k-nearest neighbors in the language model. So I think that we're already doing what you're saying to strengthen the extraction from the language model. I believe that's what you're suggesting, and it's a very good suggestion, and that's actually what we're doing.
Thank you.
Thank you very much, Mark. You mentioned the evaluation being a major problem in the beginning. Then you talked about open domain question answering. I'm not sure if this is the proposed solution for evaluation, or what are the options, how we can deal with this?
It's certainly not a solution yet. So open domain question answering evaluation is as other people have remarked, an open problem. There are no good open domain question answering data sets. The problem with question answering in general is that most questions have been asked and answered before. And if you're a language model, you've seen most of them before. And this is, essentially, this is why, even back in the days of Muck and its contemporary Trek, we did very well with bag of words question answering, because most questions that people ask are actually asymmetrical. So the question of who shot Kennedy is actually asymmetrical because nobody's interested in who Kennedy shot. I don't even know if he did. So if you answer these questions on the basis of bag of words, you do very well. It's only when you do the error analysis that you see that there is a special category of questions that you're failing on completely. And in fact, in the days of Muck and Trek, we did bag of words. And when we did the error analysis, we found that, of course, sports is the domain where you fail. So one of the questions in the test set was, who did George Frazier beat? But another question was, who beat George Frazier? And bag of words gave exactly the same answers. So it's really only when you do the error analysis that you see what's going on in standard question answering tests. So we are having to devise our own question answering tests. And we have done that in a paper that we published last year, I think, on generalizing the graph that I talked about from binary relations to unary relations. And we generated an adversarial question answering data set from that we think is along the right lines. So it's a data set that essentially consists of directional questions. And we generate that from one set of news text, identifying frequent relations that people are interested in over entities that people are interested in. And we use those to generate questions which we answer from a completely different set of text using the entailment graph and whatever methods come to hand. So I regard your question as being an important open research question to actually find a way of evaluating open domain question answering.
So the suggested answer seems to be to build hard evaluation sets.
Yes.
That cannot be resolved by bag of words approaches in general.
Yes, because
this can apply to different tasks, not only question answering.
Yes, I think so. So question answering is one of those tasks where high precision matters, because one false positive means that your user loses faith completely. So in the same competition, we were asked, what do frogs eat? And the answer came back, herons. And if you get that as a user, you never use your app ever again because you know that it's faking it.
So one question that I have is, do you have issues with antonyms? Because you have been talking about synonyms, hypernyms, hyponyms, but we know that antonyms are very bad for distributional models because they happen in exact same places where synonyms happen. So is it something that is causing you trouble?
No. The easy answer is no, because this thing is based on actual evidence from the text. So there is evidence in the text that if you look at the, for instance, in the sports domain, beating a team is an antonym in a funny sense of winning against a team. And we will find evidence that if you win against a team, you play against a team, and if you beat a team, you play against the team, but we will not find evidence that if you play a team, you beat the team. So we will not find an entailment relation between the antonyms. Having said that, the reason that this domain is so difficult is that, of course, Watford plays Arsenal on many occasions, and sometimes they win and sometimes they lose. So unless you do event recognition as well as part of your entailment mining, you will conclude that winning entails losing. And in that, you have a different problem from antonyms than the one that the language models have. For language models, the antonyms are very similar in association, so there's no directionality between them. Our problem is that multiple events of the same type may lead you to make erroneous inferences of entailment unless you're very careful. And of course, we do pay attention to dates when we're deciding whether beating someone entails winning. But without qualification, antonyms as a whole are not a problem. In fact, on that experiment that I didn't really have time to spell out, with using WordNet, we actually constructed a special antonym data set to make sure, to compare ourselves with the language model. So that was actually an adversarial data set of that kind. So we're fine on the whole with antonyms, provided we do event reference.
So there has been work that has been proposing to use language models as knowledge bases themselves, right?
Yeah.
So here you're interested in using language models just for the entailment mechanism, but you're not really interested in the prior knowledge that they have. And kind of you had just like touched a little bit on that aspect. So the question is, how do you make sure that you're using the language model just for the entailment capability and you don't really get interference from what it knows about the world from the text it has been trained on?
So it is, I mean, I'm sort of maybe getting confused. So the entailment graph embodies common sense knowledge. In fact, one of the reasons that probing text for this class of entailments probably isn't going to work is that these are the things that are obvious to every speaker of the language. I'm thinking I'm missing your question, but I can't hear you.
Okay, so you have in the text that one team won against another one, but actually kind of from the previous knowledge of the language model is actually the other way around. And I'm wondering to what extent you can get an interference there.
Oh, okay. There is a simple answer to your question. We segregate the role of the language model. If the entailment graph answers the question, then we rely on the entailment graph for its precision. If the language model has a suggestion, we only look at the language model in this very restricted role of does it think that there's something in the entailment graph that is likely to be entailed by the thing that's in the text. So there is the danger of the language model is that the language model will come up with a hyponym and will think that, and that is in the entailment graph, and but it is not the thing that the language model comes up with is not entailed by the thing that is in the text. And that is an error that will show up in our error analysis. But it's rare because of this distributional bias in the language model itself. So we're really chaining this thing down. And it's what I referred to in my first slide. We're only using the language model for what it actually learned from the text, not for what we think it might know from the text. And we hope that that's sound.
Wonderful. We're unfortunately going to have to leave it there. I know there are other questions, so let's thank Mark again for a wonderful talk.
Thank you.